So we've been given a number of ways of relating our rotational variables to our translational variables. But what I haven't so far given you is a reason why this is useful for us. So in this video, I'm going to go through a worked example that involves both rotational and translational motion. So we'll look at this problem where we have a bowling ball rolling down a ramp inclined at an angle theta, and we're asked to find the net acceleration of the ball. So reading this, we can see that it's already a force problem. So we'll start it as we do with any force problem, which is to draw a free body diagram and to find the net force acting. So we have the standard forces acting on our bowling ball. We have the weight force, and because the ball is rolling and not sliding, we have the force due to static friction acting up the ramp. I define my axes as I did for the inclined plane problems in the forces topic. And then I will resolve the weight force into its x and y components, which are mg sine theta in the x direction and negative mg cos theta in the y direction. Because my ball is rolling and not sliding, I have a couple of other things that I'd like to take into account. We also need to consider in this question that we're not looking at a point mass, we're looking at a bowling ball. So when we're looking for the movement of the bowling ball, we're looking for the movement of the centre of mass of the bowling ball. And we know that the movement of the centre of mass obeys Newton's laws. So I'll put that in the diagram, and that makes it easy for me to see that now what I'm after is the linear movement of the centre of mass of the bowling ball. So what the question is actually asking me to find is the linear acceleration of the centre of mass of the bowling ball down the slope. So now my next step is to find the net force acting, and I do that as I would for any force problem. So from the diagram, the net force is acting down the slope, and that's equal to the x component of the weight force minus the force due to friction up the slope. I know my net force is equal to the mass of my ball times its net acceleration, and I know from my diagram that my x component of my weight force is equal to mg sine theta. So that leaves me with the force due to friction. So to find the force due to friction, I need to look at what it actually is. So this friction is the static friction between the ball and the slope. So if there was no static friction, so for example if the slope was icy, then the bowling ball wouldn't be rolling, it would be sliding. So in other words, this static friction is the force which is causing the ball to rotate. And so knowing that, I know that my force due to friction is causing a torque on the ball. And then I can write that torque is equal to r cross F. So that means I need to define my r. And in this case, for me, the easiest way to define the r, so that I don't have to deal with any angles, is to have this r at 90 degrees to my force due to friction. And that gives me then that my torque is equal to the radius r times the force due to friction. And I also know from the previous video that my torque is equal to my rotational inertia times my angular acceleration. So combining those two equations, I get my expression for the force due to friction as I alpha divided by r. I'm looking for the net acceleration. So I'm looking for the linear acceleration of the ball down the slope. So I need to get this expression in terms of linear variables. So I know that my moment of inertia of a sphere is equal to 2/5 times mr squared, and I know that my angular acceleration is equal to my linear acceleration divided by r. And in this case, my linear acceleration is our net acceleration down the slope. So simplifying all that, I find that I can write that my force due to friction is equal to 2/5 times ma net times the radius of the sphere. And so substituting that back into our original equation, we get that our net acceleration down the slope, and this is the acceleration of the centre of mass of the bowling ball down the slope, is equal to 5/7 g sine theta.